Good day, everybody. I'm going to give some feedback today on the RF noise system where we are at the moment. So maybe just a preview of why we're doing this. Just a quick summary. We want to establish if the noise floor of the radio frequencies that we use as amateurs are being affected by noise, and if that floor is actually getting worse, if the noise floor is getting worse, so that it will affect our two-way communication. The higher the noise floor it is, the worse it will get. And I'll give you some details around that, what we've developed and how we want to do the measurements and how we're doing the measurements. For some reason, I cannot get this slides there. There you go. So radio frequency noise refers to unwanted electromagnetic signals that disrupt communication. These noises arise from various sources. Common sources include power lines, motors, ignition systems, electronic devices, and apparently mobile cars, charging circuits that they use now, and solar panel systems also produce a lot of noise. So how can we establish or can we measure this? We need an antenna system, a generic system. We need a receiver to receive the different at different frequencies. We need to measure a bandwidth within the frequencies itself, and then we need to measure the field strength in that band of interest. We need to do some spectrum analysis on the different bands so that we can see what's actually happening on the band. And then we actually also need to make sure that the equipment that's doing the measurements has got a very low noise floor, and so that we can actually measure the atmospheric noise that's received by the antenna. We also want to maybe do a signal to noise ratio, and then we obviously want to preferably put these stations all over South Africa so we can compare different noise levels and different areas geographically in the country, and then we can see if certain areas are getting worse or better, and if there's suddenly a noise problem in that area, we can then pick it up. Right. The monitoring system itself consists of a remote station, basically, that sits at a person's premises, preferably because we've got power and you've got internet connectivity, which is required. And I'll explain to you why you need internet connectivity. So the station needs to record the noise levels at 1 meg bandwidth from 1 meg to 30 megahertz. So there's 29 bands that gets recorded continuously every 1 minute, and then that data generates a graph on the actual remote station, the station that's receiving the signals, and then that data that is received, it gets uploaded to a master server once a day so that we can do comparisons between different stations within the country. So that's in short what the system does. We've built a version 1 of the system, which we're using an RTL SDR. Now, RTL SDR can receive up to about minus 90 dBm signal to noise. That's the best it could get. So we've then decided maybe we should get a better receiver front end, and we looked at the 12-bit versions, and that should give us maybe close to 110 dBm, somewhere there. So that will give us a better noise floor, so we can actually, for areas that's very quiet, should be able to pick up even better results. And what we're also thinking of is reducing our 1 meg bandwidth recording down to 10 kilohertz. Now that would mean we've got much more data that we want to record, and therefore we needed a bigger SD card on the actual Raspberry Pi, and that's why we decided on a version 2 that can offer the smaller bandwidth recordings, and also allows us to then upload the 12-bit capabilities to the master server. If you can also use a 3G dongle onto the Raspberry Pi if you do not have a permanent internet connectivity through Wi-Fi, for instance, and you have a remote station where you want to put this, that could be done as well. Just to explain what's these pictures, we're having graphs that is recorded. We've got the master server that can also do graphs for you. And then the unit itself has its own graphs with also spectrum capability. Take you to the next slide. So the version 2 station basically consists of an MSI chipset, which is similar to the SDR Play chipset, but not with proper front-end filters. It's got an active antenna, a Raspberry Pi, SD card, and then internet connectivity, and it's got a built-in software that's preloaded on the SD card, which then records the 1 meg bandwidths and gives you graphs of the recordings at 1 minute intervals, daily, weekly, monthly, and yearly graphs that you can get for each band. It's also got a capability to give you a spectrum view, for instance, where you can see the fast Fourier transfer of the actual signals coming in, and the hotspot view, what you've seen here. So here you can see at these frequencies, there's definitely noise, and in this frequency there was some transmissions during the day. So by using the combination of these two, you can see which is actually noise and which is actually transmissions that's produced at short intervals. So the master server basically consists of a geographical map. What you will do is you will register your remote station to the master server. It will generate a unique key, which you then have to enter in your remote station, and then the master server will allow you to send the data on a daily basis to the master server. We've also got on the map, we will show all the physical stations all over the world where they are, and then that data will then be recorded. And it's got the capability and menus where you can extract other stations' data as well as your own data. And then it's also got some graph capability where you can compare different stations' data that you can see on the right-hand side here, and see where and how this noise flow looks like. In this case, you can see there's actually signals that's widespread on different stations, and you can see the one station here, the noise flow actually increased, and in the other station, the noise level basically stayed the same. So that's a type of data that we want to see, so therefore we can understand what's happening in the different geographical areas. This is a view of how you can export the data. You can export it from a starting date to an end date, and then you can select a specific station you want to export the data. If you just want to see a small snapshot of the data on the screen, you can select this. If you click export, then it will export a CSV file for you, which you can open up in a spreadsheet and draw your own graphs with it. That's just a view of the active stations that's active, and it will show if it's stale, that means it hasn't sent data for a day, and then you can see if your station is still active or not, and when last did it send data. Let me just see why this has gone back. I don't know why that happened. Okay, so the remote station internal workings, the software itself, it receives the data from the SDR here, and then we use a utility called RTL Power, which basically you can define the bandwidth that you want to record or take a snapshot. We take about 12 readings, and we take the average of 12 readings so that we don't suddenly have funny readings that there was a short burst of noise or something like that. We then save that data into a CSV file, and then we take that CSV file data and we store the data in an RRD database. And then we also record another recording for the hotspot view so that you can see the graphs out of that. And then the RRD database then generates us the graphs, which is minute, daily, weekly, and so on, monthly, yearly. And those graphs then gets exposed on a web server on the Raspberry Pi, and you can actually connect from a browser to your Raspberry Pi and see all the graphs and stuff that your station has generated. And therefore, you've got a complete noise monitoring system in your house or in your shack, and that gives you all the information that you need for your station. Then the remote station, the master station, which receives all the data on a daily basis. It sends it around about 12 o'clock at night to the master station. The master station saves all the data in a MySQL database, and then it allows us to basically do data extraction out of that, do graphs out of that. And so you can also access the data, or you can see the graphs that I showed you in the previous presentation. It also allows you to register your station, and then it will send you an SMS with your unique key to enable your station. In some cases where you have high power transmitters in your area, you can add additional filter board, which we've designed that you can plug into the Raspberry Pi, and basically it's got a low pass and high pass filter for the HF band, and you connect your antenna here. It's got a power injector for your active antenna. It's got a one-to-one isolation, so it will give us some kind of rejection to common mode ground loops. We've then got antenna switch, which will then switch between two filters, a high pass and a low pass filter in this section here. And then we've got an antenna switch that will switch either the high pass or low pass back out to a SMA connector, and that will go to the SDR. So the antenna comes in here and the SDR sits on this side. Then we've got two IO pins that controls those two antenna switches, so it will switch the correct band in as required. This can be configured on your remote station, and it's a configuration that you enable or disable basically on your Raspberry Pi. This is just another picture of block diagrams. It's antenna, power injector, one-to-one isolation, high pass, low pass, SDR receiver, and the Raspberry Pi. This is just a picture of the RF board. Here's the one filter, here's the other filter, here's the RF switch, here's the other RF switch, and a regulator for power injection to the antenna, and here is just a DC decoupler for SDR receiver. So this is simulation of the low pass and high pass filter. You can see from a simulation point of view, I think it's a 7th order attenuation, so the attenuation is pretty good. I think it's down to 40 dBs if you look at that. So yeah, it seems to be working reasonably well. I have put it on a spectrum analyzer to check its curve. It's very close to what we've simulated here. Then this is how you register your station. You put your call sign, your website URL, and that's normally the URL. If you want to expose your local station to the internet, you can put your local station's URL in there. You put your email address and your mobile number. We will not expose obviously this data to anybody, but that's purely so that we can send you the unique key, and then we can let you know if there's some issues with your station or something. Description of your station, your physical GPS coordinates so that we can show it on the map on the master station, and your physical address, which we just keep so that we roughly know where your station is within South Africa. The Raspberry Pi images can be downloaded. So for the version 1 image, we can download this image. And this will allow you to use the RTL SDR, and using the image for Raspberry Pi 4, which is a 64-bit gigabyte image. And this one allows you to use SOAP drivers, which allows you to use SDR Play or a MIR type of SDR receiver, which is 12-bit, and this is 8-bit. That's where you can download the actual images and then burn it in the SD card and put it on your Raspberry Pi and connect your SDR receiver and active antenna, and you should be running. Okay, questions. Since this is pre-recorded, you're probably going to have to ask Hans if you can answer. Otherwise, Hans can forward the details to me, and I can reply to whoever needs more information or details on the actual system.